issue. Mr. N. Murugesan is joining us online, and he'll be reviewing the two presentations, one from Mr. Ishwar Pisalkar and one from Mr. Dheeraj Gangadharan. So I would like to invite Mr. Ishwar to give the presentation. And our chair, Mr. N. Murugesan, he's a former Director General from CPRI.
Friends, it is my privilege and honor to chair this session, which is very important. The electric mobility is, positioned as one of the smart grid component, which addresses many of the issues like generation as well as consumption. So we have two important papers. One is from Ishwar and another from another is on Tron technology. So we are happy to introduce Mr. Ishwar. Ishwar brings about 12 years experience in the renewable energy and the EV charging sector, having worked with leading organizations such as Tata Group, Reliance Group, and currently the SR Group. He holds master degree in smart grids and bachelor degree in electrical engineering. He is also a certified manager, energy manager, and a chartered solar designer for the government projects. Ishwar's expertise spans project development, implementation, and strategic planning in clean energy domains, contributing to the advancement of sustainable energy solutions across the industry. I'm happy to introduce over to Mr. Ishwar.
Thank you so much, sir. Good afternoon, everyone. I bring topic today, opportunity for battery swapping in India. So setting up a context to give you the short intro why this topic is important. Presently, EV charging has already got a lot of boost from the Indian side or the global side, and it's rightly pursuing very well. But battery swapping is really a new topic in India. So battery swapping is currently very new in India, and it's not getting that much potential what it is actually having it. So what I'm talking is about only the case study or the present, whatever the study I have done in the B2B cell. So basically the swapping industry right now focus majorly into the B2B sector. That is mostly for the e-commerce, logistics, last mile operators or food delivery partners or the commercial passengers segments. So battery swappings are mostly quite convenient than the fixed charging networks because of the customers related having the anxiety issue of the range, as well as the battery related warranty issues, as well as getting a larger time to get battery charged. So all these parameters get removed if the battery swapping gets introduced in India. So taking it through the some of the context where I'm talking about the global overview, the Indian market right now pursuing about the battery swapping. The TCO basically talks about two-wheeler and three-wheeler market right now, what pursuing and what is beneficial for the network. Then potential opportunity, or we talk about the business model that can be scalable in Indian market. And those conclusion and some key takeaways from the recently issued government policy about the battery swapping as well as the EV charging infrastructure. So global market overview talks about how the battery swapping is gaining potential worldwide. You see that in 2024, it has quietly closed about $240 million USD. So it's getting a growth of around 24%. And if you talk about the business model, so business model, there are both business models are available. That is for the captive as well as the public. But if you see, the captive one are more famous than the public one. The reason behind this is more of the standardization part and the interoperability part. So that lies more with the captive or the OEM's direction. So governments are not that much involved into this standardization process. So that's why this mostly boost going around the captive nature. And the pay-per-use model or the subscription model, both are there in the market, but subscription-based model are getting famous because the customer gets unlimited swaps in a single day. If we talk about the market, which is Indian right now industry pursuing, so battery swapping is not that famous in India, but definitely it's getting boosting because of recently launched policy. And if you see the market, the similar gain potential right now pursuing, that is approximately around 25 to 26%, and it's lastly closed around 100 CR in last 2024 year. And apart from this, there are a lot of collaboration is happening between OEMs, between swapping operators, and as well as with the aggregators that to talk about the discoms, as well as with the some software as a service providers. So as per the JMK report that says that India is having the second largest swapping market in Asia Pacific area, following up by the China, because China is having a lot of swapping network. And again, if you see, there are a lot of things that are happening in India because Indian Oils are having a partnership with Sun Mobility to deploy more than 40 Tier 2 cities or Tier 1 cities, considering the main metro cities as well. Some companies like OEM, Greaves Electric or Bajaj, if you talk about Bajaj, if you talk about Hero, all these are tying up with swapping operators to get this swapping boost more easily. And the ministry has already launched the battery swapping policy. That's because of that now the OEM partners are also seeing it that this base case scenario is more viable than the fixed charging network. Apart from this, Niti Aayog and ICCT projected that requirement over 10,000 swapping stations are required for three-wheelers and two-wheelers in metro cities, Tier 1 cities and Tier 2 cities. So that is as projected around 2030 or next 5 years, market is going to be around 70 millions. I'll take next thing. TCO talks about total cost of ownership to the customer. So this B2B customer basically are the owners who operate their fleets at larger time, and they require multiple swaps in a day or multiple boosts for a requirement of kilometers in a day. So if you see the comparison to the IC engine or compared to the fixed charging, swappable are more economical and convenient, considering the residual value of the own fleets as well, because the battery ownership goes around to the swapping operator. It doesn't lies with the customer. Then customers are more secure towards the batteries, because if any change in the batteries or the sizes or the compartment or the technology, they don't have to worry about it. So that's how the TCO looks like this for two-wheeler as well as the three-wheeler. That talks about there are a lot of difference between the fixed and the swapping technology. If I talk about the potential business models, so there are quite business model famous, that is battery as a service and software as a service. But there is one business model that's still getting recognition, that is infrastructure as a service, where discoms are required to play much vital role here, because the land and the power availability or the infrastructure availability can be much provided to this swappable operators, and that can be a kind of a plus point to the swapping operator that can decrease the price for giving it to the customer. So right now, if you see, EV tariffs are getting flourished into all the states at much cheaper level, that is around from the 4.5 rupees to 7.8 rupees. But receiving end at the customer end, that getting charged around 20, 25 rupees or 30 rupees with, including the GST. So where that lacking point is there, after charging the fixed, whole battery, that they still have to pay a lot of prices. But swapping can reduce that price because you just have to pay for the discharge amount of the battery. So if we talk about the mobility as a service, all the OEMs are already supplying this to the e-mobility operators as well as the e-commerce or the logistic partners. But infrastructure, that right now it's started pursuing with the Adani as well as Tata Power in DDL, that is Delhi, that they have given up lease their lands to these operators at much cheaper level or the revenue sharing model. And these are getting a lot of benefits that business model are getting viable, because initial investment for this swapping infrastructure is required huge amount of money as well as huge amount of battery packs. So that is one of the model that requires a lot of boost from the discom side. And components, yes. So components, right now the market is pursuing that this interchanging stations that we call swapping station, where the compartment lies for the battery swappable, these are getting now localized manufactured. So that's called the component will be having a more area to pursue this and reduce the price of the swap stations. If I talk about the conclusions, so yes, strategic partnership is required with battery swapping operator. As you see, the charging point operators in India are getting right now boost because the localization has got very far, and now they are getting more standardized, and more CCS2 is getting more standardized. Now rest of the charging infrastructure is getting vanished. Now only CCS2 based chargers are into the market. Similar way, the battery swapping operator can bring down the such flexibility or the compatibility to the swapping station once it gets aligned with the particular OEMs and the aggregators and the distribution companies as well. Innovative business model, yes, as I talk about battery as a service or the infrastructure as a service will be a more innovative model for the battery swapping business, and this might improve the lot of affordability or the serviceability for the partners. Adaptability, yes. Flexibility to the battery sizes. If single swap station can accommodate more than 4 to 5 OEMs battery, then this is going to be a game changer and different chemistry as well. So scalability point of view, yes, a lot of efforts are required to scale this into the transportation hubs or the multiple parking or the society that might give the more boost to the swapping area. Innovation, yeah, I mean this market is now only limited to two-wheeler and three-wheeler. But in coming days, as a lot of, I'm hearing a lot of things from the lot of OEMs that swappable trucks are launching, swappable buses are launching. The company is called Sun Mobility is going to launch their swappable battery station for the buses. The SANI is going to launch, SANI India is going to launch the swappable battery for trucks. So then the Montra Electric, which is recently shown in the Battery Mobility Expo, that have showcased that swappable trucks can be there in the mining area. So all these are getting famous. So why this is happening? Because of the swapping infrastructure and the PM drive policy right now launched by the Indian government. So that shows that they have given a recognition to the captive or the private players that can be, get subsidized or incentivized for their investment into the infrastructure cost. And there'll be more steps towards standardization localization of the whole battery packs has been taken forward, and they have not given any mandate for keeping service charge to the billing network or to the charging network, and they are laid down around 2,000 crores of for the EVCI development under the this swappable or infrastructure requirement, and they are given another boost that battery as an service to the grid can also be provided with respect to renewable or with respect to storage. So, I mean, that's all from my side. Thank you.
Mr. Murugesan, do you have any questions for Ishwar? Mr. Murugesan?
Yeah. Ishwar, it's a good presentation. And I congratulate you on these particular things, which because it is even my city in Bangalore, it is very popularly swapping is going on,
Correct,
and the people are happy about it. Only one important thing is that when you have many players comes into picture, and batteries of various kinds are available, is there any standardization or anything is there, or how do we do that? Otherwise, again, it will be a vendor-driven kind of things like that. So, is there any hiccups in these particular things, or how do we do that?
So, sir, in my view, this can be driven with keeping government into.
Can you talk little closerly
Yeah.
so that I
So,
am not able.
This
Yes,
push can be,
now it's audible.
yeah, so this push can be given, sir, with respect to the pushing government into the area, while they have given us a mandate that battery packs has to be developed localized and given, right chemistry for the right industry, because there are a lot of chemistries are coming into the market. Now there are solid state and then sodium ion is also coming up. So
Yes.
yeah, so all these things has to be first, make compulsory to certain OEMs that for smaller batteries, this chemistry has to be pursued, and that localization or the standardization has to be processed by the government mandate has to be given. So there the things are lacking right now, because we are speaking to a lot of officials with the Niti Aayog as well as with the BEE, but still there has to be some point where this teams has to be come up and with some innovative stages where everything has to be considered at a single point, because every OEM are keeping up their own battery packs or their own battery sizes, which making difficult for the market to pursue such kind of networks.
Have you done any similar exercise to find out what international organization like IEC have done on this direction, swapping and all such thing? Have you done any comparison or benchmark so that it is easier to implement it
So
and
benchmarking, sir,
propagate it?
so for the benchmarking, sir, I have not much gone into deepen on the battery packs. But yes, on the benchmarking, I am studying a lot of battery swapping operators. What are their needs and what are they are right now facing a difficulties to achieve more potential gain for this swapping industry. So I'm basically right now going after that area.
Huh. My humble submission is that to make this this is very easy for any three-wheeler, two-wheelers, like they come to the station, swap it in no time and go. It is
Correct.
going on nicely.
Correct.
Suppose you want to make it as in a larger scale, it is applicable to many things. You kindly see that there is the smart grid standard is there for in IEC, a set of standard where the swapping is also one of the things. You just
Correct.
see that so that you align that to particular things, so that it is easy for us to propagate and get it acceptability in a very large scale.
Correct, sir. Thank you so much.
We'll do that.
Thank you.
Thank you very much.
Thank you. Any questions from the audience? No worries, no worries. Thank you, Ishwar. Now we'll have the second presenter, Mr. Dheeraj Gangadharan. Dheeraj, yes.
Yeah. Ashima, Dheeraj has joined, no? Or,
Yes, yes, he's there here with us in person.
no, I could not follow. Has he come there or is he available there now? Okay. Friends, this particular presentation is on harnessing drone technology to transform India's future in mobility. We know that this application of drone in especially transmission line monitoring and management like that, it was well established and it is used very extensively. Now the e-mobility has started and it is in millions, going to be millions. So this application of the tracking and all such things, is very important. So we are very happy to hear from Mr. Dheeraj regarding this using drone technology for e-mobility. I am happy to introduce Mr. Dheeraj. He is an experienced process consultant with over 7 years of expertise in business process management, consulting, and digital transformation. He specializes in analyzing, designing, and implementing BPM best practices to address industry challenges and drive process excellence. His work spans process discovery, diagnostics, governance, and optimizing business process architecture for sustainable improvements. Dheeraj has a strong track record of delivering impactful solutions and strategies that enhance operational efficiency. He is also a passionate advocate for innovation and actively contribute to the thought leadership and idea generation within BPM and utility industry space. Over to Dheeraj.
Thank you, sir, for the introduction. Good afternoon, everyone, again. I'm Dheeraj, and I'm here to present on the topic, Harnessing Drone Technology to Transforming India's Future in Mobility. I'll share how drone technology can revolutionize India's mobility landscape, discuss the current context, explore key challenges, examine diverse applications, outline a strategic roadmap, and highlight the benefits of this transformative technology. So what are we discussing? We are exploring how drone technology can transform India's mobility landscape, creating more efficient, accessible, and sustainable transportation solutions. Why is this important? Despite India's global leadership in mobility, challenges persist. Traffic congestion, limited last-mile connectivity, and environmental concerns continue to impact our economic growth and quality of life. Unmanned aerial vehicles, or drones, offer innovative solutions and bypass traditional infrastructure limitations, provide rapid service delivery, and significantly reduce environmental impact. Now the question will be, how will we achieve this transformation? The solution lies in establishing robust regulations, encouraging private sector involvement, and developing essential infrastructure to unlock the full potential of UAV technology. Let's look at the context from an Indian standpoint. India's drone industry is set to reach $27 million by 2024, growing at 5.78% CAGR in the time period of 2024 to 2029. The market aims for 79.6K units by 2029, generating around 1 to 2 lakh jobs by 2030. Boosted by Drone Rules 2021 and PLI schemes, the sector sees growth in agriculture, e-commerce, and healthcare. Innovations from startups like IdeaForge and Skylark, alongside the penetration of global players like DJI and Wing, expand the ecosystem. Key progress areas to focus from an Indian lens would be regulatory reforms, pilot projects, and skill development, along with IoT and 5G integration. While drone technology offers tremendous potential, several barriers hinder its widespread adoption. Regulatory bottlenecks include the lack of standardized regulations and data security policies, creating legal uncertainties. Infrastructure gaps arise from limited drone ports and designated air corridors, restricting scalability. Public perception is another hurdle, with safety concerns and low awareness reducing acceptance. Lastly, technical barriers such as short battery life and limited payload capacity restrict operational feasibility. Overcoming these challenges can revolutionize transport, logistics, agriculture, disaster management, and urban planning. Drones are transforming multiple industries by enhancing efficiency, safety, and accuracy. Here, I'll talk about some use cases across diverse industries. In agriculture, they help with crop spraying, soil analysis, and irrigation monitoring. For construction and infrastructure, drones assist in aerial surveys, worker safety monitoring, and structural inspections. In energy and utilities, they enhance power line inspections, wind turbine monitoring, and solar farm maintenance. Logistics and delivery sees improvements in last mile delivery and transportation monitoring. For security and emergency response, drones support surveillance, firefighting, and disaster response. Finally, in environmental protection, they aid in wildlife monitoring, deforestation detection, and pollution assessment. These are just some use cases that the drones can achieve amongst the plethora of use cases we have. You can see here how drones are truly redefining industry value chains. Now, implementing drone technology across India will require a phased collaborative approach. I suggest a three-phase model for this. Phase 1, foundation, would focus on establishing regulatory frameworks, pilot projects, and skill development to demonstrate viability. Phase 2, infrastructure development, would emphasize on creating drone corridors, integrating 5G and IoT for seamless connectivity, and encouraging investments through public-private partnerships. Phase 3, scale-up and optimization, would involve expanding drone deployment across urban and rural areas, enhancing mobility through data analytics and KPI optimization. Sustainability metrics will ensure environmentally conscious growth in this phase. The North Star we are looking at is a transformative roadmap, revolutionizing mobility, fostering economic growth, and positioning India as a global leader in drone technology. This comprehensive strategy will continuously refine drone systems and maximize their impact. Coming to benefits and outcomes, the successful implementation of this roadmap will deliver significant benefits across multiple dimensions. First is efficiency gains. Drone taxis and cargo drones can reduce travel and delivery times by up to 60%. Cost reductions, logistics and operational costs can decrease by approximately 30%, benefiting through lower prices and improved services. Environmental impact. Drones have significantly lower carbon emissions compared to traditional vehicles, contributing to cleaner air. Enhanced accessibility. Drones improve connectivity in remote and underserved areas, enabling better access to healthcare, education, and commerce. Economic growth. The drone sector is expected to create substantial employment opportunities, as I've already discussed, and attract foreign direct investment, stimulating economic development. This holistic progress will drive economic growth, enhance quality of life, and boost our nation's stand in drone technology and innovation space. In conclusion, I would highlight the following key takeaways. Drone technology offers enhanced mobility, economic growth, and sustainability. It has transformative potential across various sectors, improving efficiency and accessibility. However, challenges like regulatory gaps and infrastructure limitations remain. Recommendations to address these gaps include a phased collaborative approach with standardized frameworks for urban operations and security. Private-public partnerships should drive innovation and investment, while R&D must focus on improving battery life, payload capacity, and navigation systems. That's all from my side. I'll welcome your questions and insights now.
Mr. Murugesan, do you have any question?
Thank you very much.
Thank you, sir.
Yeah. Thank you very much, Dheeraj. Have been a wonderful. I have one question. Actually, this drone technology is very successful in the transmission sector because that is easy to monitor and all such thing. Because that transmission line or that infrastructure are not intelligent enough to give you the information. So this drone is very easy to adopt like that. But here, Dheeraj, the devices are intelligent. You take your e-mobility and all such things. These are all built with communication things like that. In that conditions, why do we need a drone? Because all the drone, whatever it can able to do that, it can be accomplished by using your communication systems like that. So how do you convince the people to adopt?
So I think you are right in that aspect, but the most convincing use case that I see in the near future being adopted is basically service delivery. So if I talk about healthcare logistics as well as food delivery as an example, These are the use cases that would be adopted in the near future, if I talk about, and then we can expand the use cases to different other domains, right? So there, I don't think communication as a lens is applicable to some domains, but the near future use cases that I see are totally different, sir. So there, the applicability is huge.
No, no, you could able to perceive my question. No? The thing is that all e-mobility devices are built with basically the communication and processing, things like that. So whatever we want to achieve this, through drone can be achieved using the existing technology, whatever we want to derive at it. That's what I'm just, as a layman, I'm asking that.
Okay, no, sorry, I didn't get the question, sir.
No, no problem. Another thing is that Dheeraj, what is that initiative done by the smart grid framework IEC standard have initiated on this direction? Because that data and modeling and all such thing, it should coincide with smart grid framework standards like 61850, or you take electric vehicle charging infrastructure, or even electric vehicle. So how do whatever data you generate, through this your drone and all such thing, have you done any studies to see that that coincides with the modeling and all such things?
Sorry, I haven't deep dived into that, sir.
Okay, no, not a
Sorry
problem.
for
Just
that.
you take it from
Sure, sure,
these are
I'll
all
take
new
it up.
things.
Yeah, sure.
Not an issue. This is a new technology.
Correct, correct.
New things you are giving a dimension. These are
Yes,
all input, whatever small input we are giving. You can able to take it,
I'll take it back and
make it.
work on it for sure.
Yeah.
Thank you, thank you,
That's wonderful, Dheeraj. Thank you very much.
thank you, everyone.
Yeah. Ashima, any audience, any
Yeah,
question
any
is there?
question from the audience?
Thanks.
No, thank you. Thank you, Mr. Murugesan.
Yeah, it's my pleasure.
Yes.
Sorry, friends, I had to be here. Otherwise, I love to, on all the years we were there, and I had to come. Otherwise, I love
Right,
to see
right,
our
right.
friends.
Thank you
Thank
for
you
your
very much.
time. Thank you very much for your time.
Yeah, it's my pleasure.
Thank you.
Wish you all the best.
Thank you very much, sir. We're signing off now.
Thank
Okay.
you, Ajay and Dheeraj, once again for having made a wonderful presentation. Thank
Done,
you
done.
very much.
Thank you, sir.
Thank you very much.
Yeah. Sir, hello.
नहीं लॉग कहाँ से होता है भाई चलो बंद रहना अपने आप हो जाएगा
We'll now start with our third session, which is on the foundational blocks for smart grids. And the session will be chaired by Mr. Rajesh Bansal, former CEO of BSES Rajdhani Power Limited. Welcome, sir. Before we get on to the next session, I would request Mr. Bansal if he can give the token of appreciation to two of our authors, because Mr. Murugesan was online. So if I could request Mr. Ishwar Pisalkar. So maybe you can come down, sir. Yeah. Thank you, Ishwar. Thank you very much. Thank you. And, Mr. Dheeraj, once again. And I would request our authors to stay back to, encourage the other authors. Okay. Thank you. Please stay on till the end. Thank you. So I would request now Mr. Aditya Kumar Pati to give the presentation. Again, as informed, we'll keep the time restricted to 15 minutes and a 5-minute chair remarks. Huh?
Just take this.
Vikas, please.
Good afternoon, everybody. Myself Aditya Ganapati from Tata Power Western Odisha Distribution Limited. बोलला से मैं बोल रहा हूँ. So my topic is improvement of frequency regulation and reliability in renewable energy based distribution network through advanced inertia control and optimized fault path indicators. So here actually two topics are combined together. First of all is reliability improvement by using advanced inertia control strategy. So what is actually inertia control strategy? By the increasing of the renewable energies like solar, wind and other renewable energy sources, these energy are nowadays is very important for our society because these are clean energy and not polluting the environment. But what is actually demerits? Demerits are these energy are having low inertia. Low inertia means if suddenly load is increasing or vice versa, there is a much frequency deviation is there, and this the solar or wind cannot capable to the stability of the systems because the very large deviations in the frequency scenario. So for this we use the advanced inertia control. Inertia control is nothing but this is a battery bank or any diesel set which can suddenly give supply to the system so that the system stability remains strengthening. So second is by using the optimized fault path indicator, what will happen? The reliability of the system is increasing. So these two combined topics are combined, segregated together. These are my contents. Next, for the study, I taken the microgrid having a generation. Generation means I taken here a thermal power plant, then on the microgrid control center, then there is a load center also there, means any house or any industry who can take load from the grids. And for renewable, I taken the solar as well as wind energy. And for virtual inertia control, I taken a battery bank here, and any commercial industry also we connected together. So this is actually the overall scenario of a microgrid. This is the ideal microgrid, but here I have taken, this is the my study. I taken the microgrid like a thermal power plant as well as wind power plant and solar power plant. And for inertia control strategy, there is a loop is there. There is a inertia control loop with combined with ESSS. This is a energy storage systems. ESS nothing but energy storage system. And there is a controller strategy. What is actually controller? I have taken, normally all of you know that there is a PID control is a very useful controller in our system. So we taken the PID controller with a programming. Programming means I have taken the programming is supply demand based optimization technology. So by using this supply optimization technology, I am tuning these two parameters P, I and D so that the frequency will control. So here I have taken the solar variations, as well as the RES. This is the combination of solar as well as wind variations. Also, I have taken the load variations. This is a case study. I have taken this load variation. You can take any variation in the account. Next is our frequency deviation. In our systems, I have taken without the any inertia-based control and with inertia-based control. From this graph, left side graph, you have checked there is a red color graph as well as a blue color graph. So blue line is indicates the system having no inertia. No inertia means only solar and wind power plants are there. There is no any storage elements or any diesel sets are connected together. So that there is a deviation is large, means the overshoot is very enlarged in the systems. And second, the red graph is the with inertia control, means we have to any inertia parameters we have taken, a battery bank we taken, we have checked the value. The graph, so the red graph, there is a less variation of frequency. So next, in the right side graph, if you check the overshoot, normally it is decreased 45% from non-inertia control to inertia control. Next, I have taken the case study. Case study means we know that the inertia based is beneficial as compared to non-inertia based, but what will happen in the deviation of the load? If load value deviation or wind parameter is very and also deviation according to the wind speed, also on the solar also variation is taken. So in the case 1, I have taken a value, load means 100% load we have taken, then we have taken the 60 to 70% of the wind speed as well as the solar radiation. So if here also we check the what is our capability of inertia control. Here also we will check the red color graph is the inertia control with PID controllers. Also again another thing is there. The PID controller I have taken in the 3 methods. First one is the by using the PI controller, means only proportional and integral controller we have combined together. And the second case, this is the PID controller, and that is the both combination of proportional, integral as well as the derivative controller. And the third case is the PID means proportional, integral plus derivative controller plus again I have filter another derivative controller in the account, so that the deviation of the parameters of frequency deviation is negligence as compared to the PI controller. So 3 controller I have taken and combined together, and the performance is the PID plus, that is the 1 DD means again another derivative control taken in account. Next, case 2. In the case 2, I have increasing the wind speed, means also the load also I have taken increasing the load. First is the base load is there, and second with the increasing the load, that is the 20% enhance the load. And here also I have taken the all the controller in account. Again the PID plus the derivative controller, we get the better result as compared to the other systems. Next, case 3. In case 3, we have to also increasing the 3, means here one is increasing the load, second is increasing the wind speed, here we are increasing all the parameters combined together. Then again we have to take in account our system is much stable as compared to the others. So here actually in this paper I have taken the frequency deviations. So frequency deviation is the actually main string of the power systems. The string actually it will tie the load, the transmission, the distribution line as the load centers. So you can also this project we can also taken with islanding mode also. This maybe we can connect to the grid system or islanding grid systems. Our performance is better as compared to the non-inertia controller. Next, second is the optimization fault path indicator. So all of you know that the fault path indicator, it will indicate the where is the fault in the system. So, but there is the major things is either it is a radial network or any network, it means interconnected network. So for renewable energy based, what is the major disadvantage? If the renewable energy is connected to the system, there is a reversal, means bidirectional flow of energy. So for bidirectional flow of energy, the normal FPI does not indicate the faults. We cannot properly measure where is the fault in the networks. So that is why this is the normal network I have taken with two sources are means two generating sources are there. Maybe you can take a renewable source or any diesel source. Anyhow, so what will happen here? Actually, the fault means two parallel lines are there. One line having faults. By using the FPI, we indicate the fault in this line, and we will separate this line and charge the second line, so that the reliability of the system increase, means the total consumer is not affected to the by using this FPI. Means we have separated the another parallel lines. Then major thing is by using the radial or the non-directional FPI, it does not indicate the reversal fault. For reversal fault, either we have to taken two. Here I have taken two cases. One is the voltage and currents in the accounts. So in the forward case, the voltage and currents are in positive direction, and the second cases is what will happen? The current is in the negative directions. For indicating the negative direction of the current, I have taken the algorithm. By using this algorithm, what will happen? I have taken the positive phase sequence as the reference, as the measurement. When the fault is in the negative sides, means the reverse direction, what will happen? The reference current as lag or lead between the pi by 4 and 3 pi by 4. If the fault is within this length, this is a forward fault, means as usual or the radial network. But for reversal case, which is not in between these two angles, means if the fault is without exceeding this angle, that is a reverse fault. So we can measure this reverse fault, so that the direction, means the direction of the fault we have measured, and we will separate these the lines. Next is the conclusion. By conclusion, both the cases, first by using the virtual inertia control, we strengthening the reliability of the system, and second case we will by using the optimized location of the fault path indicator, here the reliability increasing, other cases the stability is increasing. So the major parameters in our power system, first stability and reliability, by enhancing these two phenomena, it is enhancing. Thank you, sir.
Okay, thank you. Any question? Anybody want to ask? Yep.
So, I have a question.
Yes.
You might have heard about one of the most critical fault cases, which we call it as high impedance fault. So, usually those faults are typically, invisible to the
That is invisible, very leakage current flow.
the algorithm which you have shown, it is based on
The algorithm which you have shown, it is based on the current, the fault
Yes.
performance indicator which you have shown. So how do you think in case of high impedance fault your algorithm will behave?
So algorithm is actually the algorithm is only the difference between the directional and non-directional fault. It's not the magnitude of the fault. I have not taken the magnitude of the fault. Means if it is a high impedance fault or negative direction, it will indicate what is that, because the angle is there. But your question is the magnitude of the fault.
The question is, will it be able to detect the high impedance fault?
Both cases it is valid.
Because current in the high impedance fault goes very low.
Look, but the angle is there. Means you have let fault current is 100 ampere. You are saying that the fault current is here 10 ampere, but the angle is as there. Angle is let 135-degree angle. The angle is you can measure.
And the second question I have is about the angle measurement. usually the angle cannot be measured using the current transformer. So how are you planning to do that?
Here PT also is there, not only one thing is there. PT also voltage. I have taken the voltage and current phasor both are connected together. And reference as voltage phasor, with what much the current phasor lagging or leading I have taken.
Thank you.
Anybody else?
Hi, my question is that have you compared your results with that of physical inertia control? As in the response time of physical inertia control is, I think, slightly faster. It's typically between 2 to 7 seconds, whereas the PID controller in your case is giving a response time of about 12 to 13
Yes, that is why I have taken another derivative controller in series with these systems, so that it will enhance the your timing as you have taken. It is for short time it will taken.
Okay. My next question is that so this PID controller that you have designed is for a particular microgrid. What if you change the structure of this microgrid? Will it impact the parameters of your PID control? I mean, is it as it is this control applicable to other structures of any microgrid system?
Okay, I will just simplify. Will this work, this battery-based system, will it work for only microgrid or will it work for the regional level?
It can work in other grid, but we have tested for microgrid purpose, because in microgrid actually there is less inertia. We have inertia control we use because system have less inertia to enhance the inertia, because in any alternating energy like by using of the alternator, this have the high inertia, means thermal power plant as well as the hydropower plant having the high inertia. There is no need of the inertia control here.
Fine.
Thank you.
Okay, thank you, Aditya. So we will have a...
Thank you, Aditya.
Thank you, sir.
I would now like to invite Ms. Surujana from GE Vernoma.
Good afternoon, everyone. Good afternoon, sir. Today my topic is estimation of most probable root cause using digital tools for inverter-dominated power grid. So today, let me just tell you about the agenda. So firstly, I will explain about the problem statement that we are addressing, and then I will also explain about the controller method, LVRT controller method, which is available in the literature, and then the grid compliance, which is given by the CEA. And then I will also talk about a case study which we have simulated, and then I will come up with the conclusion and the future scope of the case study that we have implemented. Okay. So let me start with the problem statement. For the past 2 days, we have attended multiple sessions in this conference. So the only one thing that we have been listening is targeting net zero carbon emission. So we are interested in decreasing the carbon emission it could be of any target by 2050 or 2070. To achieve that, we'll have to increase the IBR, inverter-based resources. All these inverter-based resources cannot just be rooftop or an isolator or an islanding conditions. It can be the carbon emission will be reduced only when we are doing the grid integration. We also have another another government program which says one sun, one world and one grid. So based on to achieve all those targets, we'll need to do a grid integration of IBR. So for that to happen, we have multiple operational challenges while we are doing grid integration of IBR. So I have listed down 4 major operational challenges. First one will be inverter protection settings, limited control algorithms, and lack of coordination between IBR and the grid operators, and fault detection and recovery. In this, the present case study that we have concentrated on limited control algorithms. So we are proposing that not just the voltage fluctuations or any frequency fluctuations are depending on the settings of the LVRT, the control algorithm settings. The control algorithm should also consider the topology of the grid, into which the IBR is connected. Okay, okay, this is the basic basic LVRT algorithm which is available in the literature. So LVRT will explain you about like we have a couple of control algorithms like LVRT and HVRT. So we have considered LVRT. So LVRT is a algorithm which will help you understand if there is any voltage fluctuation in short term, if there is any short term fault in the grid, and which leads to the voltage fluctuations. What is the ability of the IBR to stay connected to the grid instead of isolating. Okay, so if you see the graph here, the very short term fault is considered about 0.15 seconds. So the voltage is again restored back to its allowed compliance limits. So voltage limits given by the grid compliance, grid code is explained in the next slide, but it is about 10% as per the grid code India. So here it is within the limits of 0.9. So if you see the graph, in the first graph, if the area is in the area 1, then the IBR will be stayed connected and it has no voltage, only voltage disturbances is observed and the IBR stays connected to the grid. But if there is a long-term disturbance in the system, it will fall in the area B and IBR will be disconnected from the system. So if you consider the below graph, LVRT not just does the voltage monitoring, it also does inject reactive power required for the system. So as we have a huge power systems, power grids, if there is any requirement of the reactive power due to the voltage fluctuations, it must be provided only by the IBR. It cannot be pulled from the infinite grid. If it is pulled from the infinite grid, it creates much more problems. So LVRT should also will have to help, should have to help with the reactive power compensation. So here if you see for the voltage variation for 10%, which is under the limit, there won't be any reactive power requirement. But if there is any voltage swell or a voltage sag, then it is similar to the over and under excited synchronous motor. The reactive power will be injected into the power grid. So here these are the grid code compliances given by a CEA regulations. So mostly grid code will be given for voltage fluctuations, voltage regulations, frequency regulations, reactive power regulations, and harmonic distortion. So here if you see according to the grid code, frequency deviation must be under a plus or minus 1% at the point of coupling, and voltage deviation must be under 0.9 to 1.1 per unit, which is 10% voltage deviation is allowed. And even the total harmonic distortion should not exceed 5%. Even the reactive power also should not, reactive power deviation also must not exceed 5%. So these, all the LVRT designs should be in compliance with the grid codes. We have considered 2007 CEA grid code for our, now let me go into the case study that we have simulated. So we have added an IBR at bus 1 of a 9 bus, it is a normal IEEE 9 bus system. So at a bus 1, which is a generated bus, we have removed a conventional generating generator, and we have added an IBR there. And that is one scenario. And in another scenario, what we have done is we have added a transmission line between the generator and the nearest bus which it is connected to. So our main claim here is, if there is a transmission line between the IBR and to which the grid is connected, point of contact, it might cause multiple voltage fluctuations which are not predicted. So what we have done is, we have taken faults at multiple locations. One at immediate transmission lines which, to which at the point of coupling, and at a generated bus, a far end generated bus. So we are identifying how the voltage at the inverter end looks like. So we have injected a double LG fault at all the fault locations which have mentioned, fault 1, 2 and 3, 4. So we have done double LG fault in all those locations, and the fault duration is only for 0.1 seconds. The entire simulation period is for 6 seconds, so fault is injected at 5 seconds. So if you see here, the first one is at the fault at the bus 1. So bus 1 is at a conventional, far end conventional generator location. So if you see all the cases, in all fault cases, we have observed that voltage inverter at the voltage at the inverter end will have a voltage dip will be less when compared to the voltage at voltage dip when there is a transmission line. So we have considered both the scenarios, with and without transmission line. So if this voltage decrease in the LVRT, which this is very much similar to the LVRT curve. So this sluggishness in the voltage will not provide required reactive power. So these are the what inferences that we get from this results are, it cannot provide required reactive power into the system, point number 1, and it also creates a time delay into the system, and the voltage also voltage sag also might be there in the system for a longer duration of time, and the protection which has been protection setting which has been done for a normal condition might not satisfy for the voltage dip which is there, and the fault might be there for a longer period of time instead of islanding the IBR if it is not a short term fault. And so we have, if you can see the other two fault locations, it also has a similar condition. So, yeah, this is how the effect of transmission line is on the effect of transmission line if there is a transmission line between IBR and the power grid. So the main purpose of the LVRT should be it has to have a better response time for a better immunity to the power grid, and it has to be robust, and it should also have it should also complies with all grid code compliances, and also should be under it also should consider all voltage and reactive requirements, to avoid all unpredictable analysis and scenarios and all those instabilities. So what we are proposing is LVRT, in most of the LVRT settings, if you see, it will just take the reactive power requirement, or it will take the K factor, to which there is a linear, when I have shown the LVRT curve, it has a linear increase in the restoration of the voltage dip from the actual level. So it will just take those settings for voltage restoration and the reactive power. But it also has to consider topology of the grid which it is being connected to. So we are proposing to add that into the DERMS software. And no, like we have considered only a transmission line in between, but not just the transmission line, we'll just have to consider the entire topology as well. Thank you. I have my co-author, Dr. Nikhil Sharma, and also my co-author, Gaurav. So if you have any questions, we are happy to answer.
Yeah, any question, please?
Now, currently, if we can see that all the solar plant, right?
Sorry?
Solar plant.
Yes.
Solar plant is having one PPC. As per the CA guideline, any of the solar plant having generation 10 megawatt and above will be employed on PPC, photovoltaic plant control, right?
Okay.
And this solar plant is controlling, this PPC is controlling number of solar inverters, and each solar inverter having one again controller. Now this LVRT function currently coming as an inbuilt function of this
Inverter. Yes.
Now this LVRT can implement in the PPC level also.
Okay.
Right? And the PPC not only for this purpose, it is for the purpose of that control of reactive power and active power. Now, where you are targeting in your case? Because already in case of all these cases, already this part has been taken care. Which part of the network you are targeting? Separately implementation of LVRT.
No, sir. It's like in all the LVRTs, if you have seen, which is available in the market, I'm talking about the LVRT which is there in the inverter end. We do not consider the LVRT in the PPC what you have mentioned, but we in this what we have seen is LVRT which is there in the inverter end. So in all this inverters settings, if you have seen, it does not consider the network topology. So, and the variations in the network, if suppose you might have a huge, like the length of the transmission line might be different it is a practical problem that we have come across. So if the length of the transmission line from the IBR to the point of coupling is huge, then we'll have many voltage disturbances and unpredicted fault conditions, to which which was not identified at starting. Later on, after it was identified that it is caused because of the length of the transmission line between the, so that is one scenario. So what we are proposing is not just the transmission line, if we consider the entire topology while doing the LVRT control, then we might have a better results and will not have any unpredicted instabilities or the disturbances.
Thank you. Just a quick comment, because there was a question around LVRT requirement. It's always at the inverter level. Even for wind turbines, for example, there is no plant level LVRT. It's actually at turbine level. Srijana, one question is, so you had the voltage response for with and without transmission line, right?
Yes.
Practically for any plant, while you're commissioning it, you actually do set your reactor power controls based on the actual network you're connecting to, right? So the with and without transmission, I assume you use the same control parameters, right?
Yes.
And then simulated it, which
Yes.
is obviously why you'd see different response, right? But practically for any plant, at the commissioning stage, you're actually going to set the parameters anyway, right? So, so the simulation that you did, yes, it has to be grid aware, but to an extent that is already done, right? So for example is, for the same thing applies for weak grids also, right? So if your short circuit ratio is lower, you would set your inverter parameters differently, right?
Okay.
For a weaker grid. You'll actually slow it down even more, right? That's what we do in all our wind plants, right? I'm Deepak from GE. So our practice within wind plants is, of course, if you're connecting to a weaker grid, you actually slow down your voltage response because you have control interactions, right?
Okay.
So my point is, yes, it has to be aware, grid aware, I completely agree, but it's typically done during commissioning stage, correct? So, so was there anything, a different way you wanted, IBRs to be set up based on the topology? Because your point is correct, that it has to be based on topology, but is there an idea how you would do that actually, right?
At this point of time, we did not propose it yet, but we are planning to introduce line parameters in the settings of the inverter, along with the P and Q and K factor.
Okay, thank you, Sochna.
Thank you.
So we have next speaker from Noida Power, Mr. Brendra Chaudhary.
Good afternoon, sir, and good afternoon, everyone. Yeah, my technical paper is related to a project that we did in Noida Power Company Limited, related to managing of outages and the customer satisfactions. It's a related to effective solution for Indian power utility to address the customer power failure and grievances. Actually, outage management system is the customized solutions we did in NPCL. We started in the year of 2023 and just ended last year. Our motto was to develop this product to capture all the outages on the real-time basis and provide proactive information to the customers, so that the customer know where is the outages and they can plan their machinery accordingly, right? And the integration of all the available channels from where the customer can complain. So all the channels get integrated, and the backend system. Backend system like the SCADA system is there, GIS system is there, and there are some AMI and AMR concepts are there. So moving to the next. So this slide actually depict the context where we thought of. We thought these are many of the things that while the time of designing. The real-time outage detection and response that we have considered. Proactive communication through the various channels, that is maybe the WhatsApp, IVR, and SMS. Information through the AI chatbot. Information and get the customer feedback, whatever outages was there, what was the restoration time, and what was the behavior of the engineers who are solving the issues. Workforce optimizations, whatever complaints we are providing to the field team get aware about quickly once the outages happen in the system, and once any outage reported by a customer, that should be reached to the field team quickly, so that the power rectification, any fault can be rectified within the defined time. Predictive maintenance, while all the things are coming through the faulty devices, we used to identify the faulty devices as well, which are getting faulty in particular time frame. Accordingly, the predictive maintenance call raised automatically. These were the relevance. We actually evaluated many products that is available in the market, and realized we can develop the scenario in-house with the in-house capabilities, where all the local scenarios can be covered. Like obviously there will be the minimization of TCO will be considered. Integration with the existing systems like the existing running a SCADA system, existing GIS system, existing AMR system, that is AMR enabled meter and kind of things. Real-time analysis so that the decision can be taken quickly and the accordingly action can be taken over it. Local network dynamics, the dynamics that I mentioned here, according to the practice that we follow to restore the network, that also has been considered in these solutions. And the enhanced customer satisfaction while restoration of any power outages in minimal intervention, minimal duration. These are the actually architecture that is I depicted here. So on left side, there are the multiple channels through the customers can complain, customer can talk to our concerned team, customer care center. All the complaints get logged into the CRM system. If any outages happen already, that is recorded in the OMS system through a SCADA system. With the integration of GIS system, we taken the customer indexing part for each of the network elements like the feeder. So which feeder serves which customers, which transformer serves which customers. Whenever any fault happens on the particular device, it gets recorded in the system, and accordingly it is actually being broadcasted with these channels to the customers. So here there was a scenario, before scenario and after scenario. Earlier there was some arrangements were there. We actually, whenever any outage happen, outage has to be recorded manually. Outage has to be informed to the customers manually for the selected customers. And restoration happen over the call. Once the engineer goes to the site and identify the problem, once the problem has been rectified, then field team used to call back to the control room for the power restoration. And then accordingly, the control room engineer manually close the outages. So, and same manual things are happening for the individual supply complaints also. Like in various channels through the IVR, mobile app, WhatsApp, and these are the many channels are available for the recording of the complaints. Once the complaint recorded in the CRM system, it's actually passed to a field crew team manually over the call. And once the power is resolved for the particular customer, get it back. Crew actually used to inform to dispatch center team. Dispatch center team close the call, and accordingly get closed in CRM. Once closed in CRM, the SMS gets triggered to the customer for the power restorations. After implementations, we try to eliminate manual efforts. Wherever the manual efforts are there, we try to eliminate all those manual efforts. We get the power outages from the SCADA system in the real time. Whenever power outages happen, recorded in the SCADA system, it get reflected in the OMS system. Event get created in the OMS system at similar time. With the indexing that we already received from GIS system, all the customers get informed about the outages. This outages has been happened. And what will be the ERT, restoration time? What is the expected restoration time is this? The outages close. Once the outages close in a SCADA system, again it's get recorded in the OMS system. Outages has been closed automatically. Or if any problem is there, SCADA is not reporting. If somebody from the field engineers report the power has been restored, based on that, events get closed in the OMS system, and accordingly the reason for the outages get updated by control room. Then outage is closed for the area outages. For the individual supply complaints related, whenever any customers call, there is some outage in particular house, first is check the area outage, where it's linked to the area outages or not. If it's linked to the area outages, then it's not create a separate event there. It's actually merged with the area outages that is created in OMS already. And accordingly, the ERT get updated to the customers. Complaints, if a particular complaint is not part of the area outage, then complaint automatically gets assigned to a field crew through the mapping that we have created a mapping with the street. Crew actually acknowledge the complaints. Once they acknowledge the complaint, a status of the complaint get in process a stage. Once the crew complete the particular complaints from the field itself by providing the actual reason of the outages and actual fault, actual root cause of the systems, the crew has to update all the reasons from the site. Once it's updated, it gets updated in OMS system, then the CRM system complaint get closed. Accordingly the message get triggered to the customers. Customer get the WhatsApp message actually with the option of feedback, if he is satisfied with the particular resolution or not. If he is not satisfied and want to reopen the complaint, he can reopen the complaint from the WhatsApp message itself. This is the actually outcome from the implementations. In control room, actually all the outages get recorded manually earlier earlier to 6 months. Now it has been reduced to 7 to 4. Dispatch center actually communicating to crew what kind of complaint is there and in which area complaint is there and getting feedback from the crew. That has been reduced to 2. Earlier outage notification was sent manually for the ST customers only. Now it has been sent to all the customers. Average restoration time with the automations, average restoration time earlier it's come down from 1.34 hours to 1.10 hours. Area outage intimations, earlier there was no area outage of intimations we used to send to the customers. Now it's 100% with the indexing that we receive from GIS system. Individual supply complaint handling, all the complaints get handled individually 100%. Now it's approximately 80%, 20% complaints get merged with the area outages. Complaint feedback, earlier there was not feedback, any feedback mechanism was there. Now it's a 100% feedback mechanism is there. The customer can provide their feedback over the WhatsApp. Field force management, there was no digital records, all the communications happen over the call only. Now every team, crew has the mobile applications, field engineer and the shift engineer has the mobile applications. All the fault root cause is getting recorded through the mobile app and is in the systems. So, yeah, thank you. Any questions, please?
Thank you, Brenda. Since I am from utility, so I have a lot of questions for you. Just some quick one.
Yes.
So you said there are various sources of getting information about outages, including your WhatsApp, including you said your app, including your website.
Right.
What about last guest message from smart meters?
Last guess for smart meters. Actually, we started integrations with the DT meter. DT meter actually we have metered DT approximately 3,000 meters are there. So we are getting last guess outage basis for power off from the meter. Actually, we realized after studying we are getting this off message incorrectly. So recently we have approximately from 3-4 months back, we have started rolling out a smart meter on the DT meters. From DT meters,
Present one is with AMR basically.
present one is the AMR, but result was not fruitful. Now we have started deploying a smart meters there.
But even if you have a meter on TT, but the tripping is at the ACV level or LT breaker level, then there will be no last gas message.
No last guess. Actually, that is based on the feedback from the crew.
Okay.
If crew inform particular DT is down, then the manually outage creation option is there.
Then you have mentioned that proactively you inform to the consumer.
Yes.
But as soon as there is an outage, how you inform about the outage time or like within what time frame the
Proactive
power will be
informations
restored?
like, I mean to say, sir, whenever any area outage happen, we send alerts to all the customers. So whenever customers call back for any outages, actually we informing in advance there is the outage. So you need not to raise the complaint.
Time of restoration also?
Time of restoration we provide.
But how you judge that?
Firstly, we provide for 1 hour
Okay.
by default. If it's increased, then again we send the ERT.
Then when we say about the fault, there are 3 terms which are related. The occurrence of fault, the location of fault and the type of fault.
Right.
And the tripping is somewhere else.
Yes.
Fault kahin hota hai, tripping kahin hota hai.
Haan.
So are you able to detect all the 3? Ki kahan hua hai, kaisa hua
So
hai?
currently we are recording outages at feeder level, RMU level and DT level partially,
Partially, okay.
not fully.
But that is the tripping level.
That is the tripping. Tripping it,
LT feeder mein 5वें pole pe hua hai, 8वें, that is not.
no, that is not getting recorded.
And last and very interesting question. Now we have a gadget for and about the consumer rights for compensation. तो आप compensation देते हो OMS से कि 2 घंटे से ज़्यादा हो गई?
Yes, sir. We have the SLA for 2 hours, restoration of supply hours in 2 hours. Any complaint which is going beyond 2 hours, if any customer ask for the compensation, we have the provision for the compensation.
Good, excellent. Thank you. Any question? Okay, thank you.
One question, sir.
Yes.
Hi. In one of the earlier slides, you mentioned that the operator intervention reduced, let's say it was 7 to 4 or something.
Right.
So, why is the operator intervention still required in those few cases?
Yes.
What is the reason we are not able to overcome that gap?
Yes.
That's my question.
Because in control room there was earlier it was 7, now it has been reduced to 2. It's a 2 means it's a 24 hours arrangement is there. In each shift now it's 2, earlier it was 7. Because multiple time happens, whatever information we get from the site, from the SCADA site, there is a minimal chance of error also. Like in the current scenario, we have 98 point accuracy from the SCADA system. Whatever information we are getting from a SCADA system is 98% is correct. Still 2% is remaining there. So somebody actually has to inform the control room if something happened at the site, if not recorded in SCADA, or once, like I am telling you the scenario, once the fault record in a SCADA system, it getting into the OMS, and accordingly in whichever location, the particular shift engineers will be there. Shift engineers, if not get the information, if tripping is happened, but I am not receiving the information, then again he has to inform the control room that this outage has been happened here, but I am not getting any information. That actually control room people has to register manually there. Yeah. That actually for the 2% cases. Like I mentioned to sir also, for a SCADA system is on feeder side, not on field devices. There in the field device, there are many DTs are there. DTs are there, RMUs are there. So all are not communicable. We are not get information 100% from the field devices. That's why some people are always required in the field.
Yeah, but 2 out of 9, 7 plus 2, 9, and 2 out of 9 is still greater than 9. I mean, the ratio is high, right?
So
it is not 90%, I think.
Their SCADA is up to 11 kV. If the fault has happened, suppose on a particular pole of a feeder,
Okay.
so there is no way to detect it. So that has to be manually.
Okay.
that is manual.
Because SCADA is a limitation of, that's what I
Yes, substation level, 11 kV level.
is the DMS level. Even after DMS, you are monitoring anti-breaker, but still if the fault is in the part of the network, you may not be able to detect that also. So then it is manual intervention.
Okay. Okay. Thank you.
I think this is a very interesting topic, so there are a lot of questions.
See, what is the trigger for in-house development? Because many of the OEMs are available with this kind of solution.
Yes.
What is the trigger and how it is advantageous with respect to the other products?
Yeah, basically, as I mentioned, we have started Reiki in 2022. So while Reiki, we found that solutions are available there in market, but that all are based on the meter licenses, all are based on user licenses, right? And the scenario for network topology, network rearrangement, rerouting, that all are not there. Although in some product it's there, but it has the complexity, it has that overall dependency on the GIS system. If GIS system, from the GIS system, if we replicate the data, let's say in a day once time, for the power restoration, field team actually restore the particular network with the local arrangements of the lines, right? That is not getting actually recorded in the system. That is also not possible to update the GIS system in real time and get the information from GIS to OMS in real time.
No,
right?
but there is provision available in OMS, temporary cut, jumper, like that. Means why you are not using that?
Yeah. I'm coming to that. That is again, there the particular specialization kind of thing is required, right? So we have created a manual provision there. So whenever any network changes happen, the control room people used to change the particular topology in the network and record the outages there. For this, as you're saying, the jumpering and all, that's again require the proper GIS data. If GIS data properly ingested into the system, it's required to be updated on daily basis, because for the power restoration, it has to be on accurate data on GIS system, right? So updation of GIS data actually, there are multiple complexities there. It cannot be updated on the fly. It has to be updated in GIS, get validated with the QA/QC rules and business rules, and then has to be posted on the top. Then accordingly, it can be accessed to the other system, right? So those scenario, while we are designing the systems, that was a very complex system.
See, it's a fact. OMS designing, it depends upon what scope you are covering.
Correct.
If you are talking about GIS right from, then you will hardly find companies who know GIS also. On the other side, who know the mobile apps also. On the other side, they know web also. They know how to integrate with SCADA also. And how to do predictive maintenance, and how to predict the trend, and how to predict what maintenance should be done, because that depends upon what OMS scope you are talking about. So it's truly speaking, OMS is one of the package where you have to interact with all the softwares. Okay.
Yeah.
Because of time constraint, we will close
Okay.
it.
Thank you.
Yeah. Thank you.
Thank you, everyone. Thank you, Chair, for chairing the session so well. I would request if you can hand over the token of appreciation. Mr. Aditya Kumar Pati. Thank you, Aditya. Ms. Surujna. Yeah, the entire team from Mr. Gaurav and Mr. Nitin. Is not there. Mr. Birendra. Yeah, thank you. And one Mr. Vikas Gupta from a previous session. We missed him at the... Thank you, Vikas. Thank you. Miss Anjuli, ma'am, can I request you to hand over the token of appreciation to Sir, Chair, Sir? Thank you, Mr. Bansal. Thank you. One group photograph, sir, with all the authors. Surujana, everyone here, please. But Anjali, ma'am, you can stay back for the good group photograph. That's okay. Aditya, Surujana, and Mr. Birendra. A quick photograph. Nitin, you can also join. Yeah, sure. You're you're a co-author. Thank you everyone. Now we'll start with our final session of the day. And we have Ms. Anjuli Chandra, former member PERC. She'll be chairing the session. And the first theme will be India at 100 in 2047. And we have Mr. Sarasij Das as the first speaker for this session. Everything is being uploaded here.
Yeah, please start. Okay. So, good afternoon, everyone. So, am I audible? Right? Okay. So, in this presentation, basically, I will talk about the experimental setup, what we have developed in our lab of a photovoltaic power plant, which is compliant to 2800. So, as we know that the journey of renewable started with rooftop solar small scale in the distribution systems, and then it has now entered into the large scale transmission level, right? So we have now gigawatt scale photovoltaic power plants. Right? So if we look at the behavior of these power plants are quite different from our conventional classical synchronous generators, right? So what we know is not applicable now for this kind of systems, right? So IEEE 2800 has come up to address some of the interconnection issues, and it gives a lot of guidelines regarding that. So as I said that till now we don't understand the inverters well, and if we try to apply our knowledge of synchronous generator to inverters, it will not work. As a result, what we are seeing is, even though we are installing large scale plants, but we have lot of over voltages, oscillations, maltripping of protection schemes in the fields. So what are the root causes? So till now we really don't have proper models for the inverter
which are hardware validated. This is one major issue. Second one we have issue is how to have these grid code settings. Often what we are doing is whatever we had for synchronous generator, we are trying to apply the same here. And often we don't have clue, so we apply some thumb rule, or we see what others are doing, we apply that. Right? And another new thing is coming up is this grid forming inverters. So do we need them? So these are some of the questions which we have tried to address. So Grid India, as you know, that system operator, they are also facing a lot of challenges because they have to face these issues, right? So they thought that it will be good to have an experimental setup with real inverter, real control, where we can try various experiments, we can try to build various models, we can try to come up with various settings through hardware experiment. So for that purpose, 2023, they approached us to develop a photovoltaic power plant, not only one single inverter, but try to mimic the whole plant as much as possible. Right. So they have funded us for 2 consecutive years. In the phase 1 of the project, we developed grid following inverters, and phase 2, we have added grid forming inverter in that experimental setup. So this is the overall single line diagram of the experimental setup what we have developed. Currently, we have parallel of grid following and grid forming inverter. So we have this PV emulator which emulates the IV characteristics of PV panels. So PV panels are emulated through this PV emulator. Output of this going to, in this case, grid forming inverter 3 kVA. This is grid following inverter 3 kVA. Then each inverter has their own transformers. Then output of this transformer is going to 1.5 breaker scheme, where each breaker are basically motorized breaker, which can be controlled by digital signal. Then after this 1.5 breaker scheme, we have represent the collector system of the plant through LC, equivalent representation of the whole collector system of the plant. Then you have the final transformer of the plant, and then you have POM or PCC, whatever you call. Then we have a small transmission line. Right. And now within the plant, we also have a shunt reactor. So you can experiment with shunt reactor switching phenomena. We also have a fault creator. It's a physical fault creator. It's basically have resistances whose value you can change. So you can connect this resistance through a breaker across any phases you want to create balanced or unbalanced fault. And then you can close the breaker. Again, it is motorized breaker. So we have gone up to 1 cycle fault. So you can have 1 cycle, 2 cycle, 3 cycle, whatever. You can create physical fault. And this fault creator you can place anywhere in this network. I have shown it here, but it can be, it is movable. You can place it anywhere through this. Okay. Now, after the line, we have 2 options. You can connect it to grid, which is basically the wall supply, or you can connect with an real-time simulator through a power amplifier. So here the advantage is you can mimic or you can simulate any portion of Indian power grid in the polarity simulator in the software. Then you take out one bus and you connect your physical inverter plant to that bus. So it will give you a feeling that how this plant can behave if it is connected to a real power systems. And you can scale it up, like even though it is 6 kVA, when we are simulating inside polarity, we are scaling up, so we can have 150 megawatt. So this inside polarity, we are scaling to 150 megawatt power plant. So this gives you a lot of flexibility to study how an exact physical plant will behave when connected to any particular part of power systems. Right. So currently, the mode of operation, we have all these breakers by switching on and off. You can operate only grid following. You can operate only grid forming. You can operate with a combination of grid following, grid forming. Then we can also operate grid forming with load. So it's a reconfigurable system. So whatever you want to study, you can study. The features, so all these are IEEE 2800 compliant, especially the grid following inverter. LVRT, HVRT is there. We also have a power plant controller at this point. So that controller is giving set points to grid following. Then you have negative sequence injection from both grid following and grid forming. Then you can study, especially the weak grid scenario, by changing this line impedance. You can create various types of short circuit ratios, and you can see the behavior of this PV plant. So from capability point of view, what we have is voltage right through, we have frequency right through, reactive control, or automatic voltage generation, balanced current, unbalanced current injection. So whatever is available is 2800. We have tried to incorporate all of them in this network. Okay. So this is basically how, this is the picture of the experimental setup. So this was funded by basically Grid India through SRLDC. So I think this is one inverter, this is another. This is GFL, this is I think GFM. These two are inverter. This is basically the PV simulator, emulator, IV characteristics they generate for each inverter. Then this is the amplifier, you can see. Polarity is not seen anywhere. These are the filter inductors, capacitor is backside. Okay. And this is the laptop through which we can control the breakers, switching on off. Okay. This is basically my PCC transformer. Okay. So this is the setup. Now I will show you one interesting study. We have done all LVRT, HVRT, everything. So I will just present a very interesting result which can have far-reaching impact. So what we have done is, we all know that in weak grid GFL doesn't work, right? So below 5 SCR, it is suggested that don't use grid following inverters. What we have done is, we have created a weak grid scenario in the lab with 1.9 SCR. Then first we have done case 1 where we have run only the GFL. In case 2, I have done GFL plus GFM parallelly. So what we see, very interesting thing, in case 1, when I am trying to run only GFL in short circuit ratio of 1.9, the current oscillates and it, MPPT could not reach the peak point and the GFL collapsed. So after this oscillation, GFL actually shut down and it was unable to reach the MPPT point, which is quite expected, right? That in such a weak grid, it will oscillate and it will not operate. But when I am putting, for the same SCR, when I am putting GFM in parallel with GFL, then what we saw is, this is the GFL response. So here you can see no oscillations. So this gives you one very interesting insights, that whenever you have very low SCR, like below 5, if you can operate a GFM in parallel with your GFL, then GFL will work fine, right? So maybe for future, like this can be adopted for weak grid scenarios in future. So we are studying more this, but this is a very interesting results which can have a far-reaching impact. Right. So in summary, we have developed a 2800 compliant PHL setup. So here we have capability to simulate any portion of Indian grid and connect it to a real inverter and see how they will behave. We can do model validation. What will be the best model for small signal study, large signal study, transient stability study. We can actually create model and check with this experiment. So this is one advantage. Then we have also power plant controller, the interaction between power plant controller on the voltage oscillations, all those things, that their communication delays impact, anything, how to design the PPC better way, all this can be done through this setup. And also the grid code settings can be experimentally validated through this setup. Okay. And finally, what we want to do next is another important issue is the StatComs. So this is another question, that how the StatCom interact with your PV controller, with your PPC, voltage controller of your inverter. So that's why we want to also have a StatCom in hardware, and we'll try to study the interactions. Then also another very interesting target is to have a HVDC line. Rarely you see a HVDC line in hardware. So we also try to do that. Probably one MTDC will try to do in the hardwares, and we are always looking for industry collaborations. So if you find these kind of things of interest to you, your organization, please feel free to contact us. We'll be happy to participate. Okay, that's all. Thank you.
Thank you. Do we have any questions on this?
And then looking at interactions between the two, did you try that in the setup?
Both grid forming we have not done yet. We are developing one more grid forming.
Okay.
So we'll put that in parallel to two grid forming in parallel. You are asking, right?
Yeah, correct.
That we have not done till now, but that probably this year will be.
Yeah, because practically for large PV plants at grid level, you would have multiple plants and then in grid forming mode in parallel. And then for grid forming, did you basically just allow the volt-var controls a wider range and also assume that the hardware can support that amount of reactor power capability, or did you?
Basically, we had limit and we have implemented group control. So based
Correct.
on the group, it gives thing, and there is a virtual impedance control for fault. When fault happens, it introduces one virtual impedance so that the current is limited. So there is a limit on the current and everything. That's how it is designed.
Yeah, because then for grid following, just to understand, so there you basically turned off volt-var control, basically, right?
No, there also you can keep. No. We have like you are saying that volt-var control means that group you are saying?
Correct. So in the GDP, the grid-dependent power logic, for example, it's a question of how you tune your volt-var control support and the ranges you allow it to do, basically, right? And that will differ between grid following and grid forming. So how?
Range can be similar. Range can be similar. That's the, those are the questions need to be answered.
Correct. Yeah.
And especially if you want to have a grid core for grid forming, what should be included, what not. So that also you plan to do probably this year or something. But I think limits can be set. Volt-var control. But only thing is grid forming.
Only grid forming does things in a different way. Like in case of grid forming, you directly give Q set point, but grid forming you don't do. So operating region can be similar, but whether you can instruct it, that instruction may be different for grid following and grid forming. The reference what you give for grid following may not be, you cannot give in the same way to grid forming. That's what till now we have understood. We have to explore more about that.
Any more questions? Yeah.
So you showed this graph in one of your slides where you are comparing current of grid following and grid forming inverters. So just want to understand.
Can you go to that slide?
Yeah, this one. So just want to understand the feasibility of using simple LC based filters to achieve the same effect instead of going for a grid forming inverter, because ultimately it is.
If the inverter control logic is grid following, then you cannot avoid this by filter design. It's not about harmonics. It is about why grid following does not perform in weak grid.
What is the problem? The problem is grid following inverter needs a voltage signal, right? So your grid has an ideal voltage source and then you have a high impedance. Now your grid following injecting harmonics. That harmonics is going through high impedance and creating lot of voltage distortion. When lot of voltage distortion is happening, your PLL is unable to track that. When PLL is unable to track, you are generating further harmonics. So that's why your GFL basically cannot operate in weak grid. It's not about filter design. Through filter design, you cannot solve that problem. It will eventually happen.
But grid forming, because you yourself is creating voltage, so that PLL distortion, those things have no question here. So that's why if you have a GFM, means you cannot compensate or cannot substitute GFM by GFL with filter design.
Thank you.
Thank you for a very lovely presentation. I had just one question. Do you have any recommendations for the inverter on solar rooftops or small inverters?
We have not studied the smaller ones.
Okay.
So we are mostly focusing on large
Large scale. Okay, thank you. So we can have our next presentation, which is by Mr. Hari Krishna KV. Generation Planning Analysis in India's Evolving Policy Landscape, a case study of Uttar Pradesh.
Thank you, ma'am. Let me connect my laptop. Yeah, so good afternoon all. Good afternoon or good evening. So I'm Hari Krishna. I'm from a think tank named C-Step, Bangalore. So we have been doing a lot of system studies, especially transmission planning studies, generation planning studies. We were supporting the utilities at state level or regional level. For a cause like to integrate more renewables in the country, we have been supporting many utilities. Basically, we are giving technical supports to the many utilities. So when we come across some of the latest developments in terms of the generation planning, so when we come across the latest developments in terms of generation planning studies, the country are able to introduce resource adequacy and carbon markets into the some of the generating analysis. We thought of we can do some case study for one of the state in the country where to introduce some of these resource adequacy policies as well as by introducing some carbon markets into the generation planning analysis. So we have been talking about these NDC targets from past 2 days. The main intention is to reduce the emission intensity. The numbers are, we are well aware of some of these numbers. And in order to meet those targets, we have set an ambitious renewable energy targets in the country. And power sector is not, a small sector. The emissions are about 40% in the total GHG emissions in the country. So if we want to reduce emissions from the power sector, we should be having proper planning, analysis, and needs to be implemented at all level. So our paper is focused mainly on the introduction of resource adequacy in the planning studies, as well as some of the carbon markets, whatever the reliability margin has been mentioned in the resource adequacy, that has been considered. So we have considered a case study for Uttar Pradesh. Why we have considered Uttar Pradesh is this is one of the largest state in the country in terms of population, and second largest state in the country in terms of energy consumption as well as peak power demand occurred so far. So if you see the installed generation capacity in Uttar Pradesh, around 31 gigawatt of installed capacity is there in the state. Mostly comes from coal, of which 31 gigawatt, 25 gigawatt is from coal. The rest is from renewables and nuclear and very small amount of hydrogen. And if you see the peak demand occurred in the state in 23-24 is about 28 gigawatt, and the energy consumption in terms of million units is 148,000 million units. So the projected peak demand in the state for 2030 is around 40 gigawatt, and the projected energy for 2030 is around 230,000 million units. Why? UP UP is not like any other renewable rich state when we compared with western region states, especially Maharashtra, Gujarat, Rajasthan, and also the eastern region states like Karnataka, Tamil Nadu, Andhra, Telangana. These are like RRE states, we call it as like some 8 to 9 states, we call it as RRE states. But UP does not belong under any of this category. And also the RPO target set for UP is around 15%, even though the national targets are like 20%, more than 20%, especially for southern region states as well as for western region states. So considering the less renewable potential in the state, the country has set an ambitious, set a target of 15% by 23-24, but it could able to achieve only 12% of it. Due to, and also there are other reasons like the land availability in the state is, being like one of the fertile state in the country due to Ganga river basin. So it's very difficult to get land also in the state. And of the total potential in the state, it could able to install only 18% of the RE potential in the state so far. The potential is around like more than 30 gigawatt of solar, but there is no wind potential in the state. With the introduction of RA guidelines, that is the resource adequacy guidelines, and also the carbon credit mechanism, this will bring more constraints in the system, enforcing minimum reliability as well as internalizing carbon costs. So this is like a significant impact on the generation cost. This may pose significant impact on the generation cost as well as operational constraints. If you see the situation of UP, it has got like high demand growth. If you see past couple of years, like from past 6 to 7 years, it has got a very good high demand growth as well as low installed capacity. And with this new policy guidelines, making it important to analyze like different pathways, how can the state can go for more renewables in terms of like achieving RPO targets, as well as with the RA guidelines and also the carbon market mechanisms. So we tried to address some of these challenges with some of our analysis by, I will just go through the methodology as well as some of the outcomes we got from this analysis. So we did production cost analysis for the state by using open source tool called GridPath. So here we did like a base case production cost analysis for the year 23-24. Some of the input parameters like normally what we give the input parameters for any production cost analysis like generation capacity, their contracts, hourly power demand profiles, technical, operational as well as financial parameters, and also the RPO targets have been given as input parameters for any production cost analysis software. And in order to validate like whatever the analysis we are doing, whether we are going in the right track or wrong track, so we need to validate with some of the already what has happened in the state numbers, like for example whether the RPO targets are the number of units the state has consumed so far is in line with our model outputs. So we need to validate. That is like our base case analysis. Here we were able to get like unserved energy. The total CO2 emissions can be calculated based on the number of units of power generation, and also the RPO targets and per unit cost of generation can be assessed from our base case analysis. Once we do with the base case analysis, we update our model for the future year studies. The future year studies here is like for financial year 29-30 has been considered. And we ran with two different scenarios. One with high carbon tax scenario, the second one with low carbon tax scenario. In the high carbon tax scenario, we have considered the carbon tax of around $50 per ton of coal usage. And in the low carbon tax scenario, we have considered $10 for per ton of coal usage. So again, the input parameters are like we have given projected hourly demand profiles for 29-30 and other technical parameters, financial parameters, operational parameters for all the generating stations have been given as input parameters. And we ran capacity expansion analysis for 29-30. And these are some of the key outcomes, like what is the proposed RE capacity for the state, as well as energy storage systems required for the state by 29-30, as well as the investment costs in order to implement these projects. Again, we ran production cost analysis, and we have come up with like a least cost optimal generation capacity mix required for the state for 29-30. 30. I mean, again, the key outcomes are not much difference from the previous methodologies. So when we ran the production cost analysis for financial year 23-24, as well as capacity expansion for 29-30, these are some of our outcomes. In the base case scenario, around 85% of the state energy has been met through coal power plants. Either this could be through the contracts from other states, as well as the plants which are existing in the UP, Uttar Pradesh state. The hydro is very small, as well as the renewable capacity and also the nuclear capacity. All these things are very, very small. If you see the contracted capacity for the state for 23-24 is around 34 gigawatt, even though the installed capacity is around 31 gigawatt. I mean, the additional 3 gigawatt has been procured or contracted from other neighboring states. And the energy requirement for the state is, as I mentioned, like 1,47,000 million units. And the unserved energy from our model, what we could get is around 1,497 million units. And the total emission, CO2 emissions will be around 120 million tons. And only 12% of RVO target could be met of the state. And the per unit cost of generation is around 5.1 rupees per unit of energy. And if you see the outcomes for, or the outputs for 29-30, when we ran with the different scenarios, the low carbon tax scenario as well as the high carbon tax scenario with the 10 rupees per ton of, $10 per ton of coal as well as $50 per ton of coal for these two scenarios, the model is throwing as an additional capacity of renewables in the range of like 36.3 gigawatt of renewables required in the state by 29-30 in both the scenarios. But the energy storage requirement has slightly changed from scenario 1 to scenario. The energy storage requirement in the scenario 1 is around approximately 22 gigawatt, but as well as, but in the scenario 2, it will be around like approximately 24.5 gigawatt. With that, the total installed capacity in the state will be around 91 gigawatt in scenario 1, but in scenario 2, it will be around 94 gigawatt. Total energy requirement, this is again like input parameter. If you see the energy delivered in scenario 1, the RE capacity will be around 47%, the non-RE will be around 53%, but in the scenario 2, it will be equally distributed among RE as well as from non-RE sources. We could also find some surplus RE generation capacity in both the scenarios. This can be converted into carbon credits when we are talking about carbon markets and carbon credits. So this can be converted into carbon credits with an average per unit cost in scenario 1 is around 5.23 rupees per kilowatt or per unit of power. But in scenario 2, it will be around 5.25 with slight changes of 0.02 rupees per kilowatt when we compare it with both the scenarios. On the right side, you could see some of the dispatch profiles. What we have mentioned here is in the first part, you could see some of the unserved energy when during the peak, one of the peak day in UP for base case analysis. But in on the top down, the rightmost profile, you could see peak demand profile for 29-30. So the key insights from this study includes like in order to achieve 50% of generation from RE in UP by 29-30, the state needs to add another 36 gigawatt of renewable energy and approximately 25 gigawatt of energy storage systems in the state. Either it could add in the state or should be having this much contract capacity from the neighboring states in order to meet 50% of energy from the renewable sector. And in the emission reductions, like if we introduce carbon taxes, we could still go for some more reduction of the emissions. With a carbon tax of USD $10 per ton of coal, we could reduce 7%. But otherwise, if you go with the $50 per ton of coal, we can reduce another 3% of carbon emissions into the atmosphere. The financial gains, like whatever the carbon credits we could get, this can be sell outside, either with, this is still an evolving topic, carbon markets and carbon credits, all these things. So if we can sell the extra generation from the renewable plants, maybe during the non-peak demand during those times, so we could still get some good money out of it, like around 649 crores can be generated under low carbon tax scenario, but otherwise in the high carbon tax scenario, you can still generate around 874 crores of money if you can introduce these carbon markets in the system. And we are making sure that like RA criteria is met, like there are some indices, normalized energy not supplied is should be less than or equal to 0.05%. We kept this cap in the model. And this, whatever the revenues we have generated can be utilized for grid modernization. Either it could be like a grid modernization or to go for more renewables, or to improve the financials of the power sector can be use this money. So yeah, so that's all from my end. Thank you.
Thank you for your presentation. Do we have any questions? Yes.
You consider the renewable energy, and did you consider it as a clean energy with SMRs and other technologies, which doesn't have to be traditionally solar and wind? And with that, was that considered as a decarbonization lever or a?
So as of now, we have considered the RPO targets, more like the government of India has come up with new RPO targets, like 43.3% for all the states, even though there is no mention of like which state has to go for this much of RPO targets. But SMR, this is like a new topic, recently has been introduced. So as of now, we have not considered the nuclear, more addition of nuclear. But otherwise, we have considered solar, wind, hydro, and also, mostly these categories we have considered so far.
And you had to run the analysis at a hourly dispatch level, but did you also try to kind of run it at an annual level to see like what has been the suggestion, and and it will tell the real need, should we even go for hourly dispatch or not? I'm just wondering if you have done annual analysis as well parallelly, or?
No, so for capacity expansion, you can run hourly dispatch profiles. It's too difficult, cumbersome, mechanism. But otherwise, capacity expansion we ran day-wise balancing. So it's very difficult for us to run hourly balancing for capacity expansion, as you said. But yeah. So annual, if any, we are doing this analysis for a couple of states. They also asking us to give, annually. How much they need to develop their generation capacity instead of giving one number for 2030 or 2035. So they were also asking us to give suggestions like how much they need to add each and every year until 2030 or 2045. But yeah, it requires its own time and efforts. So that in any case, that is required for any of these utilities.
Maybe the last question, did you also consider any water-related aspects? Because traditionally, if you were not going to retire some of the fossil units, and if you have to consider the water consumption of those, and if there is any constraints that you had put yourself to see, the choice of technologies on 2029, 30 or even further for your analysis.
Water requirement for thermal plants?
Yeah. So basically, if the thermal plants continue to operate, but then water sustainability aspect is accounted, let's say.
Yes.
So if that has to reduce, so the usage of water will become key. And if that is a constraint, would the choice of technology or more retirals would be chosen? And would be interesting to see how the analysis show as the result. And by the way, what was the application you used?
GridPath. There is an open source tool called GridPath. GRIDPATH.
Okay, thanks.
GridPath. So this is like, just to answer your question, maybe on the water part, I agree there are some states like Karnataka, we have observed like some instance the state thermal plants could not be able to generate power due to water constraints, especially in Karnataka. A few years like there was very drought in those areas and they could not able to get water from the dams. And a lot of disputes are there in the water mechanism also in states like Karnataka and all. So there are some instances where they could not able to generate power due to water shortages. But in our model, we have not considered those aspects. Maybe going forward, let us. I mean, those features are not there as of now. We are restricting only the power sector. We are not looking into other areas and all. So let's see. I mean, going forward, maybe. Yeah. Maybe. You have some question? Yeah.
Expanding the renewable energy and all those things. So in your studies, have you considered the consumer side as well? Because why my thought is coming, I will explain you. Like industries, may not be readily use renewable energy because of intermittent nature. They can use green hydrogen maybe. But was that consumer part is considered in your analysis?
So yeah, good question. But no, we are going with the regulations or policies as described by either CEA or state governments. As I said, like the state has come up with its own RPO target, like to achieve 15% by 23-24. Even though other states are already way beyond, 15%. Or states like southern region states are, most of the states are already achieved their target and they're beyond actually more than 20%, 23%, 22 or 23%, like Karnataka, Tamil Nadu, all these states. So we stick to our analysis, for these policies. If the state has come up with a policy, so-and-so discoms, so-and-so areas or whatever it is, like states has to be met their RPO targets by so-and-so year. So we are going with those numbers. But actually, we are assuming that like they might have considered the consumers' perspective. They might have taken input from the consumers and all. So because these are like regulated entities. Like if anything comes out of any regulatory electricity commissions, like ERCs we call it as. So that has to be obeyed by all the entities within the state, as a discoms or generation companies or transmission companies or distribution companies. They need to obey their rules and regulations. We are assuming that like they have encountered all these aspects.
Okay. So I had a question. Are you considering contribution from rooftop also while considering your scenarios?
Yes, ma'am. So as part of, as I said, when I said like 43.3% from renewable energy, so there is a breakup again from solar. What is the contribution? Wind. What is the contribution from hydro? And also rooftop PV. I mean, the government of India has come up with all these segregations. So 43.3% is inclusive of all these categories.
Okay. And second question is, you are considering carbon tax of $10 or $50. First, you should consider it in rupees. Why do you want to consider it in dollars?
I mean, the model is built by some US agencies. So, I mean, in the paper we have mentioned rupees only. Like we have converted.
Okay. So I just wanted to know that you are saying there's a revenue potential of say 649 crore or something. But has it offset the carbon tax which has been paid? After that, this is the revenue, or is it a standalone revenue? You are paying additional carbon tax.
So if we found any extra renewable energy generation in that particular state, they might be having a lot of contracts with many renewable plants. It may happen that, and there is a clause now like we cannot curtail any renewable plants in the country. I mean, maybe 1 or 2 times it is okay by mentioning that grid security.
On grid security.
Security and all. But if you go beyond, again, they will be knowing like why they are curtailing.
No, what I was trying to say, have you offset the additional money paid by the utility? How much revenue potential there is after paying the carbon tax and getting carbon credits? I mean, they will, have you considered that?
Can you repeat your question?
They'll be paying carbon tax on the coal. And also, additional money. And even if they get, this renewable credits, how much is the offset of the carbon tax by this?
So this is like additional cost any utility can get. if they have any extra RE generation, they can sell it to the neighboring state or the deficit state. So this is the money they can get, I mean any utility can get out of it, if they are having extra renewable energy generation.
Usually when there is peak here, there will be peak in other states. When it is off-peak, it will be off-peak in other states. So it will be difficult to sell renewable energy. Or are you considering
that mechanism has to come up? I mean, still we're still in the discussion stage only for carbon market and all. I mean, BE is working on this. Maybe by 26, I mean by next year, I think they may come up with this carbon credit and trading mechanism.
Yeah, it will come by December 26.
Yeah, even by 2026, they're not targeting power sector. They have considered
December 26 for the industry.
Some other 9 sectors they have considered, but there is a, I mean, long time is there to consider even the power sector.
Thank
if
you
you
so
see
much.
China and all, they have already introduced the power sector, the carbon mechanisms. But yeah, we are, I mean, we have tried to attempt this mechanism here, and maybe.
Thank you so much.
Yeah. Okay, thank you, ma'am.
A round of applause for him. So I'll call the next presentator, Aditi Narang from Energy Exemplar. Integrated Modeling for Sustainable Energy Transition.
Good evening, everyone. My name is Aditi, and today I will be presenting on integrated resource planning for renewables and green hydrogen modeling. So our energy systems are undergoing a major transformation with ever-increasing demand, which is, just increasing really rapidly, as well as the increasing penetration of renewables in our existing grid network. And also there are these targets that India, some very ambitious targets that India intends to achieve. First target is that by 2030, 50% of the installed capacity should be renewables, and another target is that by the year 2070, India should achieve net zero emissions. So this calls for a holistic approach which provides essentially a blueprint for the power system of the future and all other major power system pieces spanning generation portfolio, transmission, as well as distribution. So there are some other constraints and some other factors that we need to take into account before we proceed with these planning exercise in order to achieve these ambitious targets for our country. So for example, we need to take into account what are the different types of technologies that we want to consider. Is it just renewables like solar, wind, associated battery, or some other green hydrogen fuels also? What kind of batteries do we want to incorporate in our system? What should be the sizing and what should be the siting of these batteries? As well as whether there are any energy mix constraints, any other regulatory and policy compliance that we need to take into account. Then we also know that since we are going to have so much renewables in our system, how we are going to take into account the intermittency associated with these renewables, whether we are also including the transmission aging, some congestion analysis, and how do we plan to upgrade our transmission infrastructure, as well as our ever-changing, ever-evolving market structure. So this is where IRP, or integrated resource planning, comes into picture. So it is essentially a digital twin model that provides, that performs the capacity expansion exercise that provides us with the optimal investment plan for a cleaner, reliable, and a more cost-effective energy system. So the IRP, or the Integrated Resource Planning Model, is a unified energy system that supports not only the existing generators in the grid, but also is able to integrate the renewables, could be our solar, wind, batteries, as well as green hydrogen, any other associated gas, as well as the supply chain of our gas infrastructure, the transportation of our gas infrastructure. So all of this in our unified energy system is co-optimized in this integrated resource planning model. So we also need to ensure proper modeling of all of our assets that we plan to include in this model. So that would include, for example, for the renewables, taking into account the intermittency, because we know that, for instance, for solar, the power generated at 12 p.m. will be much higher than the power generated at 5 p.m. So, how do we plan to include this uncertainty by the means of some stochastic modeling, perhaps? Then for our battery, what are the different types of technical parameters we need to include, such as, minimum, maximum, initial state of the charge, what is the self-discharge, how the capacity degradation is happening over the years. And not only that, since we are performing a capacity expansion exercise, we also need to take into account some financial properties like build cost, economic life, and weighted average cost of capital. Then comes our new technologies such as green hydrogen. So for that, again, we need to include the technical parameters like ramp up, ramp down constraints, what should be the maximum production, what is the efficiency, is it meeting the industry standards? So these things are taken into account, as well as, whether this green hydrogen fuel is directly being sold to a market, it is further utilized for gas production, or, it is stored for future use. So all of this encompasses our integrated resource planning model. It includes what will be the different aspects in the model and what should be the inputs from the user side, which I have just discussed. So now that we have our model, what are the different outputs that I can expect when I run this capacity expansion exercise? So firstly, I would like to see from my, the output of my model is that which technologies are chosen to be built, to be augmented, or to be retired over the years. And not only that, what is the, or how much for that matter, is the optimal energy mix of all these thermal generation, renewables, solar, wind, associated battery, and green hydrogen. So how much of these resources make up our optimal generation mix? Then we should also be able to see from the output of our model that when these capacity additions, augmentations, and retirements are happening over the years. So I should be able to properly see whether it's, a 5-year augmentation plan, or my capacity expansion is happening every year based on the increasing demand. So all these considerations should be there in the output of my model. And then finally, maybe I have multiple generation candidates for a particular demand profile. So I should be able to get the output that where is the asset most needed across the grid. So all of these questions should be answered by my model. So now, how is this optimization actually performed in the capacity expansion exercise? So essentially, we take into account the capital cost of the expansion of the capital cost for the expansion of the new generators or the new transmission lines, the augmentation cost of the existing generators, as well as maybe I'm retiring some older thermal generations. So I have to take into account all of those capital costs, as well as obviously the production cost is also taken into account. And this is formulated as a mixed integer problem. And the objective is to minimize the overall cost of the system, which considers production plus capital cost. So this optimization of the mixed integer problem I have done in Plexus, which is an energy optimization software. And I'll just like to take you through what is the model setup and what are the results. So a subset of the IRP model in which I have considered a hybrid model, you can see that there are some solar assets, wind assets, it is connected to the grid. I have a 4-hour battery that is connected. And then I have my hydrogen system where you can see that at the electrolyzer, hydrogen is being produced. It is further being used for ammonia production as well as stored for banking purposes. And then finally, for my ammonia demand, it is either being transported to different demand markets or is being stored for banking purposes. So as an output on an annual basis for this model, you can see that I can find what is the net bill for my different types of generation assets, what is the bill for my solar assets, wind assets, how much battery I should build over the years, what is my electrolyzer net bill, as well as the ammonia plant and hydrogen storage. So these results are only for the year 2025, but when I perform a long-term expansion exercise for a planning horizon of 20 years or 25 years, the annual results of what is the optimal generation mix and optimal build for each of the year will be available to me. So these are the results on annual basis. So now we can look at a more granular, at a more operational level. So here you can see the generation by different solar and wind assets. So whenever there is high solar irradiance available, I have more solar energy production, but there are certain phases during the day where there are valleys and the energy production is not so much. So this is exactly where we would expect our battery to work. So the battery is charged whenever there is surplus power available during the day. And then, as you can see here, it is discharging whenever we have seen there were some valley points. So this is all about this case study in which we have seen the capacity expansion as well as the renewables and storage operation. So to give you a quick summarization, in this model I performed renewables, hydrogen and ammonia modeling in the form of an integrated power and gas system modeling. We are able to model regulatory and policy compliances, including any renewable energy targets, any emission targets, and any other reliability measures. So optimal sizing and placement among few other things were output of this future expansion and investment planning exercise. And then we are also able to model for uncertainties and intermittencies associated with our renewables, as well as determine what is the optimal system operation and storage resource allocation happening. Okay. Thank you.
Thank you, Aditi. So do we have any questions for Aditi? Yeah.
So I'm assuming that you have made multiple scenarios. What if the capital cost of a particular technology comes down drastically?
Yeah.
Or alternatively, the fuel price goes up? And I would like to kind of have that answer. But the second question that I have is also, so hydrogen production in terms of full life cycle, did you account while you were doing it, or you assume basically, okay, hydrogen is produced by a certain system and then it comes at a certain dollar per, a volume of an hydrogen. So what were your assumptions on hydrogen modeling was the other question.
So to answer your first question, definitely whenever we change different types of inputs in our model, whether it is cost or whether it is any technical parameters, the output will definitely change. And so this optimization that I'm performing is based on MIP formulation. So whatever is the least cost solution for this MIP problem, that will be thrown out as the output. So yeah, if you have any particular scenario in mind, then yeah, I can definitely tweak the inputs and I can show to you that how the results are varying. So just as a small example, if my battery cost, the build cost of my particular 4-hour battery is, for example, 2x as compared to my 2-hour battery for which my cost is just x. So definitely in the output, I'll be able to see that my battery of capacity 2R is being built much more than the battery whose build cost was, 2x.
Yeah, thanks.
Have you done it on a actual system for any state or for use this Plexus for planning?
Yes.
Which state have you done it for?
Well, we have done it for the state of Karnataka. So
Okay.
this analysis has been done, yeah. Well,
Okay.
the model that I used was just a dummy model, which was a subset of the integrated, of a much bigger IRP model. So yeah, with just some dummy numbers.
So can you tell us what you came up with for Karnataka? Just a brief.
Well, on top of my head, I'm not very sure of the numbers, but
Okay.
whatever were the constraints that we had put in the model, that by the year 2030, if I am supposed to achieve my renewable targets, so I was able to achieve those targets by building more renewables in the system and subsequently retiring the coal or thermal based generators.
Yeah, but when you retire coal or thermal based generators, you may not be able to ramp up or ramp down very fast. So how did you manage the grid stability in case of outage of any solar and wind?
So for the outages, again, outages and other factors like reserve margins and LOLP, so all of those are also given in the model as input, and whatever result I get from my capacity expansion exercise, as well as on a granular level from the I can see that how the generation dispatch is and how it is affecting the grid. So all of those outputs are available.
Okay, thank you. Yeah.
So you mentioned location also, right, as one of the options. So there's an implicit understanding that you're running a power flow also within your optimization. Is that true? Or?
Yeah.
So you're running a DC power flow essentially,
Yes.
because you're using MEP power flow, right? The second question is on the battery. Did you consider, you mentioned degradation there, right? So degradation depends on DOD, right? It also depends on the actual duty cycle, right? The C rate, all of that. So did you model all of that? Because it's tough to fit it into a...
Yeah, so no, all those factors were not modeled for determining how much the capacity of the battery is degrading. I've just given the degradation profile as an input to my to modeling my battery itself. So I know essentially that, for example, in the year 2025, what is my battery capacity and what is the degraded battery capacity, let's say, in the year 2026.
Okay.
Maybe one last
Yeah,
question.
yeah, sure.
So again, back to the scenarios. So typically, when we want to make a credible pathway on how I have to investment plan for my balancing authority, as an example, so I might have to consider multiple scenarios. So it leads to the robust optimization technique that you might be aware, right? Like, which is, okay, irrespective of these variations, I think this is the best optimal technology that I can choose. That gives the optimal space and then, a specific solution set, and of course with few levers. But did you try something like that, and does Plexos has those capabilities?
Yes, definitely. So there is very detailed stochastic modeling available in the software. So basically, I can create the stochastic object for whichever object I want to, or whichever asset I want to consider. There will be, some variations. For example, if I'm considering the variation in profile of my solar or wind, or whether I'm considering variation in my demand, so I can create the stochastic objects for that. So that will take into account and when you perform the optimization, there will be, you can choose how many samples you want to work with. So again, performing that optimization, stochastic modeling, you can do that scenario analysis.
Thanks.
Okay, thank you. I would like to call Himanshu Kumar from Grid India to present his paper. Can we have it in 10, 12 minutes? We are running out of time.
Okay, see you. इंटरनेट कनेक्ट करेगा नहीं कनेक्शन के बाद कुछ दिक्कत हुआ उसको चेक कर सकते हैं
Keep the mic as close as possible.
Okay. Okay, good afternoon ma'am and good afternoon everybody. So my paper is on exploring renewable dynamics through synchrophasor technology. As we heard in this session today, many of people talk about integration of RE in the system. That's where dynamics come into pictures. All the problems about RE, low inertia, fault right through, all the things we talk about can be managed by studying dynamics, what is the RE dynamics. And so to illustrate this through real life examples, I have chosen one case of one event, which major event in India, which happened on 17 June. And I have chosen this event because it has many unique features, like we have lost around 16.5 gigawatt of load that day, which was, I think, after 2012 major event in India. Many line got tripped in this event. We also observed very high voltage dip in the system, and this voltage profile was different than usual we observe in fault, because in the fault either it is delay recovery or sharp decline, but in this case both we can observe sharp and then delay voltage dip in voltage. And this is happened because in this event we observe a new phenomenon where the induction motor started stalling after a certain voltage level. So one of the load center we observed a sharp increase in MVR, which caused the voltage reduction to around 0.47 per unit in the system at different substation. I can see in this PVT. So during this event we observe what was the behavior of RE which is already connected in the system. So as you can see, this is the total RE generation pool in our RE complex in Rajasthan, mainly 5, and now we have 7 pooling stations. So we observed that due to decline in voltage, there was reduction in active power. But as per the CA connectivity standard, he should have recovered 90% of his generation within 1 second. But that was absent from this data of these plants. So we little bit dive into the more plant-wise analysis of the system. So in this picture, we observe that this is the plant connected at Bikaner. So when the voltage reduced below its LVRT trigger point, this dotted line, we observed the generation started declining and whole plant disconnected from the system. So this is the totally different behavior of the plant from what is required as per the standards. Also in the second plot, we can see the MBR injection of the plant. It continuously injected the reactive power in the system, which causes the over voltage in the system and tripped many 400 kV and above line during this event. Also, we study the a plant from the different pooling station, such as Bhadla 2, and in that plant we observed that the plant didn't trip, but it was not able to recover it 90% of the pre-disturbance generation. Also, its reactive power injection into system was not as per the standards. Also, we have STATCOMs in those regions. We observed that although the STATCOM help us stabilize the voltage, but still due to the frequent fault in that area, we are not able to utilize the whole dynamic reactive power of the STATCOM because it was already exhausted. And also, we did a model validation study on one of the plant. This model was submitted to us during the first time charging, and we use PMU data to validate this model, and we also configure all the settings as per the plant settings at the time of the event. And we observed that although initially its behavior was as per the real time of real data, but after 2 or 3 seconds in the actual plant, we observed the decline in active power, but in simulation there was no such decline in the active power. So this problem may be because either the model which was submitted to us was not accurate, or there was some protection issue at the plant level. Also, there are some key learnings from the event and some way forward which we think will help us make more resilient and reliable renewable grids. So what we observed during the event was voltage issue, a sudden drop in voltage due to stalling of induction motor load. So we always heard about the generation mix in the system, but I think we need to also consider the load mix in the system because as our climate is changing, and so load in the system also, their composition is also changing. So during planning stage, instead of using a static load, we need to focus on the composite load in the system. And also we observed the RE tripping as we discussed earlier, because voltage was not low as compared to the place where the event has occurred. So RE should not trip around 3 gigawatt. Also, we observed the delay recovery in many RE plants. It should recover within the 1 second, but it did not. Also, the voltage ride-through capability of plants was not as per the CA connectivity standards. Also, reactive power deficiency. We observed that the stalling of motor started absorbing the reactive power, but due to reactive power deficiency at load centers, voltage decreases further and reaches 0.74 per unit. Also, in the model validation, we see the expected and actual RE response were not aligned with each other. So, what is the way forward? So, we need to strengthen the voltage ride-through capability through regular audits, also checks their protection setting and all. Also, we need to, I think, increasing RE in this NR complex, we need to deploy more SYNCOM, STATCOM, SVG-like device which can support the reactive power in the system. Also, we need PMU placed at the many key substation and distribution networks to analyze what is the load composition in case we are again meet with this some kind of disturbance. Also, hybrid RE and storage can help in stabilize RE fluctuation. The grid operator can use this storage in the as a primary as an ancillary services, and that will help us in stabilizing the frequency and the voltage dip in the system. Thank you. I'll be taking any question.
Any questions? Thank you so much. It's very interesting to know that in the, generation studies, you should also consider the load mix.
Yes, ma'am. This event actually we also got to know that this kind of situation can arise in the future.
With stalled loader modes.
Yes, in planning phase, we have to use now composite load, and we are actively pursuing it, the CRC and CA to do this.
Yeah, that's very interesting.
Actually, maybe just as a point, I mentioned the stalled induction motor loads, typically they are considered as part of RAS schemes. So for example,
which scheme? Sorry.
Remedial action schemes. So in utilities like Entergy, for example, there are quite a few papers published by them.
Yes.
Where they specifically do the physically based load model, because the zip models don't really tell you, the details about what types of loads are actually there, right? It's just numbers, right? They actually do physically based load models also. So they actually have an inventory of induction loads specifically because of this specific issue. Because once they stall, they consume huge amounts of reactor power, right? So it brings the voltage down even more.
Yes, actually in the load mix we have different type of also motors. Some motors have high torque and low inertia, some motors have low torque and high inertia. I think in PSS we have some generic model to do this kind of a study. So we have also done for this event using composite load. Any question?
Thank you,
okay,
Mr.
thank
Himanshu. So I think we have come to the end of the session.
Yeah, thank you. Thank you. Ma'am, I would request if you can hand over the token of appreciation to our speakers. Mr. Sarasij Das. Mr. Hari Krishna. Not many in the room right now. Yeah, thank you very much. Aditi. Big round of applause for Aditi. And Himanshu. Thank you, thank you.
Request all the speakers, please come on the stage. Sir, request you for a group photograph.